So I met some of you in the lab yesterday for hydrothermal synthesis, and I'll be meeting the rest of you. So it's nice that we get some presentation on it. So for those of you who haven't seen it yet, when you go in the lab, you'll see what's behind the power bombs and all that stuff that we talk about in the lab. So
is that your lab?
it's the crystal cave, you know, where I go when I'm Superman or whatever. Okay. Hydrothermal. All right, so you know the word conjures up geology, geochemistry, and so on, and indeed it's because of the fact that hydrothermal comes from the fact that there are these hydrothermal vents in the ocean floor. Here, right, this is a better pointer. And you get these plumes that are rich in different transition metals like iron, even hydrocarbons like methane. And you can reach temperatures of up to 350 C underneath the ocean because you have the pressures to stabilize those temperatures for keeping water that hot. And as the plume comes out, it comes into different interfaces like, say, carbonates, which change the pH of the water, or it comes into much cooler waters, like 2 degrees Celsius. And upon doing that, you get to crystallize a lot of different minerals. And so this is an example of the largest crystals on Earth. These are gypsum, which is calcium carbonate dihydrate. And these are grown these are in Mexico, in the Nica mine in Chihuahua. And these are not in a fluid, but in fact, they're coming from the hydrothermal vents. And again, they get into a cooler region, and that's why they're able to grow really, really large crystals. And so I'm just going to show a video. So Daryl brought up Bell Labs, so I'm going to show you a vintage Bell Labs video about quartz crystal growth from hydrothermal. And the video is quite long, so I'm just going to be skipping around as I do this. Okay, let's see. Hopefully we have audio. Oh, we do. This is vintage, okay? This is. You'll see all the troubles we go through as crystal growers.
Eons ago, our scorched earth began to cool, and mountains formed. And in time, strange minerals, tempered by heat and pressure, came into being. With the coming of man, some of these took on special value, like quartz crystal.
All right, nice quartz. All right.
Greek artisans for its icy brilliance.
This is what Bell Labs wanted it for, which is
the same result.
to get an electric response from it, and then use it in telecommunications.
A new significance. Today, tucked inside vacuum tubes.
Vacuum tubes?
Are tiny and vital crystal plates, which work as ingenious electronic filters. The crystals vibrate, giving each signal a wave beam.
All right.
And about the only source of natural high-grade quartz, which the Bell telephone...
Brazil, that's where the,
more and more
back then,
years.
they used to get the quartz from.
The greater part of this natural crystal must be thrown away because of its irregular shape and flaws that show up when the crystal is sliced. By the time it is finished, it will exceed the cost of pure gold. How to keep costs down and supply unlimited? This was the challenge offered to chemists and engineers of Bell Telephone Laboratories and Western Electric. Working together, they set out to beat nature at her own game, to create low-cost quartz, flawless and abundant.
That's what we were doing in the lab yesterday, right? Well, nicer balance in this.
They took inexpensive quartz chips and poured them into a specially designed autoclave, the chemist's pressure cooker. Then came a solution capable of dissolving the quartz chips. On top of this went a rack of tiny crystal wafers, seeds on which the man-made quartz would grow.
And so they go through several trials.
With the passing of hours into days, the scrap quartz would dissolve, moving up to the cooler part of the autoclave to deposit itself as a solid on the tiny seed plates. Then the seeds would grow and grow, or so the scientists hoped. Sometimes, after days of waiting, the seed plates mysteriously disappeared without a trace.
So this is the experimental part.
Emerged virtually unchanged. Or the crystals would actually grow, but each one was deformed by cracks or strange bubbles. It happened on occasion in these early experiments that the great pressure needed forced sudden discouraging leaks in the seal. As in all research, there were many disappointments.
Go you smoke your camel.
Would not grow without a perfect seal.
This is 1962, okay?
By studying the results of many tries, the experimenters discovered the right combination of temperature, pressure, and time. The cracks, the bubbles, and the leaks were beaten at last. The research job was done.
Yay. All right. So then they go on in the video, actually, if you want to see more of it, and where they actually scale it up and they get these just humongous crystals of quartz. And so this was pioneered at, indeed, at Bell Labs. You see here, these are the really large crystals that they get once they scale up, when they bring in the engineers. And they're the largest in the world, were actually made by the Toyo Communication Company in Japan. You can see these large underground hydrothermal apparatuses that they built in the ground. And so last year when I gave the talk, actually Sang Chung from Rutgers told me that the person who had, so those were probably actors in the video, the one smoking and everything. And the real scientist who, who developed this and pioneered this was Robert Lattice at Bell Labs, and he was really the inventor of the quartz crystal growth process. So the photo and the quote from that is attributed to him is this: that everything is made of something. If you don't have the material technology, you lose the device, you lose the system, and you lose the application, which I think is a very nice sort of theme, right, for us that are interested in materials. He also wrote one of the first comprehensive books on crystal growth as well. Okay, so the outline for the rest of the talk. So I'm going to just give you the basics of hydrothermal, tell you a little bit about sort of the physical chemistry of hydrothermal synthesis, talk about the apparatuses themselves, the autoclaves, and then towards the end I'll talk about some of the research in our lab, looking at iron-based superconductors and how we use hydrothermal to grow some of these materials. Okay, so what is hydrothermal? So so I was looking through the history, trying to find a good definition, and I found several, and it changes over time, actually. So first, it was a heterogeneous reaction. You have to have a solid of some kind and a liquid, and preferably it's an aqueous liquid if it's hydrothermal, hence the hydro part. And you need to be under high pressure and temperature. The pressure part is not so important. I wouldn't really call hydrothermal a high pressure technique. I would rather say that it's a high temperature or high temperature technique that keeps the solution from evaporating. So chemical reagents are subjected to the action of water. So the mineralizer is the water. It's typically a solution that has base or acid in it. And at some point they wanted to define it as going above the critical point of water, which is 370 degrees C. You don't have to actually do that anymore, because today the commonly accepted definition is that you just take your solution above the boiling point of water, 100 degrees C, and above 1 atmosphere of pressure. There are some related terms. Sometimes in the literature you'll see solvothermal, and all this means is that you've replaced water with methanol, ethanol, glycol, some other solvent, because maybe your material is water sensitive, so you want to use another solvent. And mineralizer, you see this often. That just was the term meant to indicate what the geochemists were using to dissolve the actual minerals, okay? All right. So the first crystals were actually grown in 1845. You could grow quartz and hence get some of these gems, precious gems, like emeralds and rubies. Also, that was used to leach ores. So this is a so-called Bayer process for extracting pure aluminum metal. And then it was starting to be used for actual crystal growth. Very important type of materials that were grown were these microporous materials known as zeolites, which are used a lot by the petrochemical industry. Here's a picture of a zeolite. And also, you can actually grow transition metal oxides, like barium titanate, using hydrothermal processes. A lot of the times, though, you'll see in the literature that oxides that are grown through this method tend to be small, on the small side. So here you have zinc oxide nanorods, for example, that can be grown hydrothermally. So it sort of all depends what you really want. You might have heard of so-called metal-organic frameworks, or MOFs. Here's the very famous one from Omar Yagi, MOF number 5. That's also, you can prepare these through hydrothermal or solvothermal techniques. You can also access metastable compounds. For example, there's this funny compound, tellurium 2 iodide, that you can stabilize through hydrothermal techniques. And if you want nanocrystalline materials with well-defined sizes, maybe you want one particular face to grow at the expense of others, you can use surfactants or other types of chemicals in the reaction to control that. And so that's another nice control that you can get from the fact that you're in solution when you're doing your crystal growth. Okay. Oh, and here's a quantum material that was grown hydrothermally. These are nanowires, so maybe not so important for this crowd, but you can in fact grow samarium hexaboride hydrothermally. Okay, so what are some of the advantages of hydrothermal, say, with respect to other high temperature techniques? You're typically working within this regime here, 100 to 500 degrees C. So if something is not stable above 500 C, you could possibly work in this under these conditions. You could work towards getting lower concentration of defects by just optimizing the temperature or the time that you grow your crystals. You can get purer materials in some cases, and it's actually a pretty low energy process if you think about it, right? You're just, you're heating up these pressure systems in an oven, and so it's not really that energy intensive, nor is it cash intensive as well. Okay, well, it's cheap. All right. So what kind of materials can be prepared? Is the Bayer process showed that you can get the native elements like aluminum. You can make oxides, sulfides, and selenides. In our lab, we make sulfides, selenides, and complex oxides like phosphates. And you can make a whole host of other type of materials as well. Okay, so the solvent is what mediates the crystal growth. What's happening with the quartz that you saw in the video there? So it's a mineral, and typically, if you put it in water, you shouldn't anticipate that it actually goes into solution at all. But under hydrothermal conditions, the properties of water itself changes so that it can actually dissolve minerals like quartz. And so one of the things that changes is its viscosity, and it also changes its polarity as well. So since viscosity is inversely proportional to diffusion rates, you can start to think about how diffusion will affect the crystal growth. And as I said, the polarity here given by the dielectric constant helps with the dissolution of certain solids. An old alchemy line, like dissolves like. And so if you're trying to dissolve something like silicates, which are covalent as opposed to being highly polar, you need to change the properties of water from being polar to less polar. Okay, so, and indeed, if you look at this table here, so this is water, and it has a dipole moment. It's one of the most polar solvents known, right? Now, if you look at its temperature, the viscosity and its dielectric constant versus temperature, you can see that in fact you start to drop its dielectric constant a lot as you start to heat up above its boiling point. And if you get above you get close to the critical point, it's effectively not really a polar solvent anymore, right? And therefore, it's able to dissolve nonpolar oxides like silicates. Okay, for those of you that are interested in hydrothermal, you want to avoid water maybe because your system reacts with the water as opposed to growing out of it, you can choose other solvents out there that are very popular for now what we call solvothermal. We have DMSO, dimethylformamide, DMF, and these have higher boiling points, so you can actually go to higher temperatures as well without worrying about overpressurizing too much. Now you will be limited by other factors like the autoclave system itself as you go out to temperature. So not only are you limited by the solvent, but also the apparatus in itself. And we'll talk about that later. So these are not as polar as water, but they're pretty polar with respect to many other solvents out there. So these are typical ones that you can look out for, ethylene glycol as well. These would be good for if you want to avoid protons, which we'd get with glycol and alcohols. Okay. Now, what about sort of choosing how much you're going to fill up the autoclave with water, whatever solvent, and what temperature can you go to and what pressure can you go to? So this is a very popular phase diagram that is printed out for hydrothermal synthesis. Yeah, sometimes people call it a bomb because these are sometimes called acid digestion bombs. It was a Gordon conference about two years ago where Ken Poppelmeyer told us we should stop calling these things bombs because there was some problem where they were talking about bombs on the airplane. And they were obviously talking about hydrothermal, and some people got worried and so on and so on. Anyway, so call it a vessel or autoclave. Here's pressure versus temperature, and this is percent filling of your autoclave. And so, for example, if you're at 10% filling of the autoclave, you can certainly go above the critical point of water here at 390 and still be okay. Whenever you get to this dashed line, that means that the vessel would rupture. Okay, so 70% filling, you could only go up to about, somewhere below 500 degrees Celsius. So yeah, think about the filling level. However, a lot of hydrothermal synthesis happens really between 150 and 200 degrees Celsius nowadays. And here you're not too worried about the pressure that builds up, the vapor pressure that builds up above the liquid there. Okay? So it's usually pretty safe as well if you're in this regime. Okay, so this is just a cartoon of what an autoclave could look like and sort of components within it. So the nutrient is called is the solid reagent that you put in here. And you can put in a lot of reagents that are soluble in water, of course, nitrates, carbonates of certain metals, oxides, hydroxides. And even if they're not soluble at room temperature, they will solubilize as you heat them up, some of them. So you have to think about what your reagents are going to be. You can actually even put in metals in there if you want it to be the source of the metal, because under hydrothermal conditions, the metal will oxidize. There's a diagram that's called a Porbet diagram for transition metals. And if you look at it, sort of how Darryl was showing, the different oxidation states that are stable for different oxygen partial pressures, the same can go for solutions. There are different oxidation states that are stable for various pHs of the solution itself. So you should look into that to think about, can I use a metal? Should I use a metal if I'm trying to do hydrothermal synthesis? The mineralizer, simply enough, is just can be the water. But you typically add other stuff into it. For example, you could add a hydroxide, like potassium hydroxide, sodium hydroxide, ammonium hydroxide to make it basic. Or you could add a little bit of hydrochloric to make it acidic as well. And then the autoclave in itself is typically a stainless steel vessel. The nutrient will sit at the bottom. You fill it up with your mineralizer. And, we don't do this in our lab, but you saw from the Bell Labs video that you can indeed put seed crystals in there. And if you apply a temperature gradient, you can actually grow very nice crystals using this technique here. And one last thing is the inert liner. Okay, now to talk about those liners in a minute. Because you don't want the mineralizer to come into contact with the stainless steel vessel itself. Okay, so some of the physical chemistry of hydrothermal. It's still an active area of research, I would say. What the thermodynamic variables are here is temperature, pressure, and I would say also the pH here, which is going to be important for the chemistry. And the studies usually there are mostly in thermodynamics, and there are some in the kinetics of hydrothermal. Okay, so the number of moles of the solute, which is the nutrient, changes as you heat up your autoclave. And so you get a saturated solution, and so we're going to just write out the Gibbs free energy as a function of temperature, pressure, and the number of moles of the C components that you put into the autoclave. And so we can write it out dg as this expression here. And then we're just going to go to a state where we have constant temperature and pressure here, so that we can only consider the chemical potential of a certain component I within the hydrothermal conditions here. And so in the end, we're only interested in the chemical potential. And we can write out the Gibbs free energy as the sum of the chemical potential of component I times the number of moles of component I. Okay, so let's consider just a two-component system. A is the solute, B is my solvent. And as A dissolves into B, we call this A1. And so my Gibbs free energy here is going to be the sum of the three products for the three different components that we get, A, B, and this solution of A and B. Okay, and all of this is just to get to a final expression here that the change in the Gibbs free energy, we're really interested in just the change in the terms between the solute and how much solute goes into solution. And it's just, oh, things disappear. Oh no, I had animation. Okay. Okay, so what we're interested in is how does the free energy change as a function of the number of moles of my solute that I started out with. And really it's just going to be the difference between the chemical potential of A1 and A. So when A1 is less than A, that is, there's less of your solute in solution, then your Gibbs free energy is less than 0. Hence, this is a spontaneous process, and your solute should start to go into solution. All this means is A dissolves into B, okay? And this is how it starts out. Okay, now the chemical potential of 1A, which is how much the solute has gone into solution, is greater than your solute itself. Then delta G is greater than 0, and this is a non-spontaneous process, and hence now A starts to crystallize out of B. Okay, so this is when you start getting into the crystal growth now. And of course, if they're both equal to each other, then you reach an equilibrium state, and there's no more phase transitions. So in hydrothermal, what has to happen first is this, then this here, crystallization, of course. And you can see from the Bell Labs video that part of the problem was, when they pulled out the seed crystals and they were gone, is you probably didn't know when you were here, right? And so this is when you're playing around with the temperature and the time of your crystal growth to make sure that you've now gone in the reverse direction. Okay. So again, this is another schematic of an autoclave. This is from, forget where I got this one from, but you can have seed crystals and you have your autoclave with your nutrient and your so-called, sometimes it's called the charge zone and the growth zone. So it's sort of similar language that's sometimes used in chemical vapor transport. So in your charge zone, the chemical potential of A1 is less than A, so the spontaneous process is for this dissolution. And then in the growth zone, you want the reverse to happen. Now, if you don't have seed crystals, and you don't have a temperature gradient across your autoclave, one way that you could make this happen here so that you can get crystallization is, there are a couple of things you can do. One is the pH changes dynamically as you heat up. And so once, say, the pH goes above 8 or something like that, then it reverses this relationship and you start to seed crystals and then have crystal growth. Or another one is upon cooling your autoclave, you start to now have this relationship and you get growth. Okay, so sometimes the growth won't happen at temperature, but rather upon cooling your solution. Okay, actually I'm just gonna skip this and go right to this one. This is the phase diagram that we saw earlier. We've seen a lot of phase diagrams, and so those lines that you've seen drawn out that don't have necessarily data point, remember, constrained by the Gibbs phase rule, are given by the degrees of freedom that you have in the phase diagram, constrained by the number of components and phases that you're looking at. So here we're just looking at pressure versus temperature, liquid, gas, and again, this is just the percent filling of your autoclave, telling you where you can go in temperature. Now, practically, where you're constrained will be in the autoclave as well. Oh, before I get to that, let me just say that there were other phase diagrams that were popular in the literature back then. These were very popular in the Russian literature, actually, I guess during the Cold War when both sides weren't really speaking. And what they were doing was different from a lot of Western phase diagrams, which was to have concentration of sodium hydroxide. They called this the mineralizer. So this was just changing the pH of the solution versus a ratio of two oxides. For example, this was zirconium oxide versus over silica oxide, and they were getting various types of phases and mixture of phases as well. And so these are also very useful if you can find them. Okay, what about kinetics? Because we talked about thermal. So kinetics is not very well understood. You can imagine it's hard because you're working in these stainless steel autoclaves that are either buried in the ground or something, or or in the oven. But in general, there are some points that you can think about, which is that the growth rates of crystal faces increase linearly with supersaturation. So if you have, as you heat up your solution and your solute starts to go into the solvent, if you supersaturate it, then that will aid in growth of certain faces. Activation barriers is what we think about. That's the energy term you think about for kinetics. And these tend to be about 10 kcals per mole, 40 kilojoules per mole, roughly, for diffusion and dissolution of the solute in the solution. If you're comfortable with EVs instead of kilojoules per mole, that's what, 400 MeV? I think of 100 kilojoules as roughly one EV. Okay, so, but the actual largest barrier for crystal growth is not the dissolution of your material in the solvent, but rather just the crystallization process, just the process of actually going in the other direction of A coming out of B and forming those crystals. That's the bigger kinetic barrier there. If the solvent is not part of the crystal, a lot of times you saw these zeolites I showed briefly. These are these microporous materials. A lot of those zeolites and the MOFs as well, they'll crystallize with the solvent in them, actually. So it's called the solvent of crystallization. And it definitely takes part in the process of crystal growth. But if it is not, say you're working on an oxide, a sulfide, or something like that, then the rate can increase for low concentrations. And last thing I would say is that pressure does not affect crystal growth significantly. I think, again, like I said, hydrothermal sometimes is referred to as a high pressure technique, but I think pressure is not really the variable that is so important in the crystal growth. It's more, again, going to be the temperature and chemical variables like pH. Okay, so some of the practical problems with hydrothermal. So an autoclave, first it has to be inert to acid bases and oxidizing agents. Otherwise you'll either evolve gases upon reaction with the vessel or have other problems. Of course, cracks or something like that could, or leaks. It has to be easy to assemble, disassemble. Sometimes this is not so easy, as you'll see in our lab. The temperature gradient for growth, you don't have to have a temperature gradient necessarily, but you can have that with some hydrothermal furnaces. And again, leak-proof and hermetically sealed. If it's not hermetically sealed, then there's no hydrothermal, solid thermal to speak of. It'll just evaporate immediately, and you'll be left with just your solute at the bottom of your autoclave. And you have to have, of course, your furnaces and ovens need to. You need to know what the pressure and temperature are in them, and able to bear the pressure for long periods of time. And so sometimes the growth can be a couple of days. Can be a week. We've done some that are more than a week, and some people can do several weeks. So it should be able to hold that time. Okay, in the beginning, chemists were using glass actually to do hydrothermal synthesis. So it seems a little bit dangerous, and I think it is. So people don't do it that way anymore. You can seal water and your solute in Pyrex or quartz. These are approximately the pressures that you can take in in such an ampule, about 6 bars. Even then, I wouldn't even go above. Personally, I try not to go above like 3, just for anything. And temperatures about here. Then came some innovations in hydrothermal using mostly the PAR type, which is what you'll see in the lab, type of autoclaves that are stainless steel, the so-called 300 series, that can go up to 200 to 350 bars temperatures. I say 250 here, and that mostly has to do with the liner in the autoclave. In our lab, we also have this so-called Turtle cone type seal, so you can actually go up to higher pressures, 5,000 bar, and about 750 degrees Celsius. So you can go above the critical point of water in this type of vessel. All right, and the liner. You can have titanium, silver, or platinum. Of course, you have to think about whether your liner itself would react with the solvent or the mineralizer. So silver and platinum are pretty good for that. I would personally avoid titanium, since of course you can make so many titanium oxides. Teflon is what we use in our lab. The only problem with Teflon is that you're constrained to about 300 C. We don't go above 250 in our lab with Teflon. And so these are typical components that you get from a PAR bomb. This is, autoclave, and this is 45 milliliter Teflon cup. And you have the cup itself where you load all your reagents, and you have these little plates in case you get a leak in the autoclave. They're there as a safety mechanism, and then you get a spring-loaded top that, when it starts to actually boil, it seals the Teflon cup, and so all the pressure is autogenous coming from the bomb itself, and so it's self-sealing if you put all the components on correctly, so that you don't lose your solvent with temperature. And then you have some other fancier ones. Most of the ones in our lab, you can just simply hand tighten. You don't have to crank it too much. But there are some that you can go up or tighten more than just using your hand. Okay. The other one that we have in the lab uses the so-called Turtle cold cone autoclave, which is a different way to do the seal here. And so it's just metal on metal, and you don't have to actually, you do screw in this part here, so you'll do that in the lab. But this one is the one that allows you to go up to pretty high temperatures and pressures. And so this is our high temperature, high pressure LECO hydrothermal furnace. You have 2 tube furnaces. So it's actually 2 furnaces. and both of them are 2 zones, so you can apply a temperature gradient across this autoclave shown here with the tuttle cone seal. So this one we can do maximum pressure of 4 kilobars, and the vertical design allows you to do temperature gradients if you wanted to. So I have to give credit to Stephanie Gunevik, my student, who is actually helping with the practicals too, for putting this together. We inherited this from my colleague Brian Eichhorn, who bought this in the 90s, and it was sort of a mess. It wasn't working. It was very dirty, and Stephanie cleaned it all up and got it to work. So now we have that in the lab. Other things that you can do, actually. So if you wanted to actually do fast hydrothermal, fast solvothermal, to say if you were interested in nanomaterials, you can actually use all Teflon autoclaves and put them in a microwave. And so this is if you want to do rapid preparation of materials. I've never used it myself, but pretty popular. Okay, so now I'm going to talk about how we've applied some of these techniques to research in my lab, so on iron-based superconductors. Sort of starting point here is we're very much interested in these layer type of chalcogenides that you can intercalate with different species in order to change the physical properties. So we're solid state chemists, but we really care about physical properties of materials. And so this is Frank DeSalvo's, Ted Jabal's work, where they inserted long chain amides, for example, to really separate tantalum disulfide by a lot. And this is a work of Simon Clark more recently, where they intercalated lithium in a liquid ammonia in order to raise the critical temperature of iron selenide from 8 Kelvin to 42 Kelvin. So it's a pretty remarkable technique. It not only charge dopes into the lithium selenide layer, but it also plays around with the structure, the crystal structure, so that it separates the layers apart. And so we were inspired by that to do that similar chemistry in our lab. Now we're not going to use liquid ammonia. We're going to actually use water to do this intercalation. Let me just back up a little bit and tell you about iron-based superconductors if you're not familiar with them. There are many families, and all of them have something in common when it comes to the structure point of view. And that is whether you're talking about the arsenides or the selenides or sulfides, and that is their square lattice. If you take away everything else, they're really just a square lattice of your transition metal, of your iron here. And so in the simplest one, which is iron selenide, I put CH here for chalcogenide because you can also do this with sulfur. It's a simple primitive tetragonal space group, square lattice with the selenide above and below to make tetrahedral coordination of the iron. And so I like it not only because it's easy to work with, but it also, I think the simplicity makes it easier to study. And so what we're trying to do in my lab is sort of promote, so there's iron sulfide and selenide, but we've been making also versions of cobalt and other transition metals, and I really couldn't find a good term for it, so I had to make one up. Sorry to make more acronyms for you, but tetrahedral transition metal chalcogenides, or TTMCs, are based on square lattices, and they also have van der Waals gaps between them to do intercalation chemistry, exfoliation type chemistry, like the type that Dave Mandrews talked about yesterday. And just to compare them against transition metal dichalcogenides, which can, of course, have polytypism and change their coordination, but in principle, they're always hexagonal base metal sublattice as opposed to square. And so I think that difference between them makes them very interesting. These are much, much, much more well studied, of course, because it's been grease and lubricants for a long time, and now they're quantum materials. But hopefully one day these will become just as studied as these here. Well, iron selenide has been a lot. Here's an example of something very exciting that can happen in iron selenide. If it's grown by MBE as a single or very thin films, there's a single layer of thin films, you can actually raise the TC either up to 65 Kelvin on strontium titanate. There was one report I read about 200 Kelvin, but I don't know exactly where the consensus is now. But you can see that actually what's very important here is that square lattice of the iron here and how possibly it could be being changed as a function of the strain or something like that on the substrate. So I sort of became obsessed with square lattices, and in chemistry department I have to sort of explain why square lattices are so cool, and so I show them this molecule C4H4 that is a square, and it has 2 electrons and 2 molecular orbitals, and this double degeneracy is unstable towards the Jahn-Teller distortion. And so since it is unstable, it'll either deform to to a rectangle upon coupling with a certain vibrational mode. And I like to say to chemists that are more based on molecules and that, they don't look at solids so often, is that something similar can happen in the solid state that's very exciting. So this is from Roald Hoffman's How Chemistry and Physics Meet in the Solid State, where you can open up a band gap, say in a string of s orbitals to make a dimer, like H2, like hydrogen, right? And Hoffman and Wolfgang Trammell postulated that this can also happen if you occupy certain symmetry zones in the square lattice itself. So, for example, the M point in the Brillouin zone could lead to a Peierls type distortion, either to an armchair configuration, tetramers, or zigzag. And so, as physicists talk to us about nematicity and other types of exotic physics like that, I like to think about it, I guess, from a chemical bonding point of view of trying to force square lattices to be unstable into one of these type of bonding configurations, like stripes, for example. Another sort of reason I got interested in these selenides is that you can intercalate different species in between, including magnetic cations like iron. And Dirk Jorent found that upon hitting its critical temperature from magnetic susceptibility, in the field-cooled zeta, you can get this anomaly here. And Jorent postulated that this was an example, possibly, of ferromagnetism existing in this layer, proximate to a superconducting layer here. And they postulated that you could form the so-called spontaneous vortex lattice within the iron selenide because of the magnetism in the hydroxide layer. So we decided to make these compounds working with Jeff Lynn, because Jeff Lynn is very much interested in these spontaneous vortex lattices in magnetic superconductors. And so we prepared, this is an example of a hydrothermal preparation. We wanted to make the deuteroxide because we needed deuterium so that it didn't scatter the neutrons incoherently. And so you can do that by just making a lithium deuteroxide salt with iron metal. Usually, if we're making selenides, this is a good selenium source. So not only does the element work, but you can use something like selenourea, which breaks down to SEH- in solution. And typically, a hydrothermal reaction will be 5 days in D2O as opposed to H2O. Between 120 and 160 degrees C, and you can get nice, this is a polycrystalline mass of lithium hydroxide iron selenide. The crystals that you can grow from these are very small if you use this process here. So sub-millimeter for sure. What we've decided to do to try to grow larger arrays of these lithium hydroxide or deuteroxide iron selenides was to first sort of do a sort of a hybrid technique here, where we made, through high temperature techniques, the potassium iron selenide, which already has these layers, and then under hydrothermal conditions convert it to the lithium deuteroxide. And so that we did that. So actually this is part of our little lab exercise. It wasn't for selenium, rather it was for sulfur, but in any case, for selenide you can see that we can, from hydrothermal, we can make superconducting materials. These are for the single crystal conversions. These are the susceptibility curves. And these are for the powder samples. So I would say only in the polycrystalline samples were we able to reproduce Dirk Jorent's results of this anomaly at low temperatures that he attributed to ferromagnetism in the hydroxide layer. My student Shuxuan Zhou, who some of you met in the lab, was able to take this potassium iron selenide with excess lithium deuteroxide and convert them over to this lithium deuteroxide with some iron on the lithium site, iron selenide. Let me finish up. Okay. So this is just neutron diffraction data that we use to show that, first of all, you want to, of course, know that you have the product and not something like iron oxides in there. And so neutrons, synchrotron X-rays, all of those techniques are really good for that. And I'll just skip over to say that we extended the chemistry over to sulfur. So we thought, selenium's so interesting, but sulfur hasn't been as explored. And then you hit up against the iron or sulfur phase diagram, and the problem is that on the phase diagram you don't have what you want, which is the layered iron sulfide. And so in our lab we started out with our trick of making the thermodynamically stable phase by congruently melting potassium with iron and sulfur to grow these crystals, and then hydrothermally converting them over to the pure FES simple one, the lithium hydroxide one, and some other hydroxide intercalated phases. And so you can use solid state techniques to get here, and then hydrothermal to access the rest of them. And so that's what we're exploring in my lab. And these are examples of some samples that you can get out of them. They're very micaceous, and you can indeed use the Scotch tape method that we saw yesterday for ripping layers from these as well. So the sulfide is superconducting. It tends to be lower than the selenide, about 3.5 Kelvin. It looks to be a somewhat different superconductor than the iron selenide. These are, what you'll see in the lab tomorrow as you convert it over from the potassium iron sulfide, a gold-like mass, to in its reflectivity, and over to something that looks like a dull gray one when you do hydrothermal. And this is just crystal structure-wise what's happening. You're taking out potassium under hydrothermal conditions, and you're stabilizing it, we think, through hydrogen bonding of the lithium hydroxide to the iron selenide level itself. So I'll just, because I don't want to keep you from your coffee break, of course, just show you that we are able to make some new superconductors this way. These are the lithium hydroxide iron sulfide superconductors. And a lot of the samples we weren't able to get above the TC that you could see in just a simple iron sulfide. But in some cases we were able to actually get a little bit above to pick up the temperature to 8 Kelvin. But you can see this is very different from the iron selenide, where upon intercalation they're able to raise it from 8 Kelvin to 42 Kelvin. Here the most that we could do is about 8 Kelvin from about 3.5. So sulfide seemed very interesting to make. It turns out that it's harder to make higher temperature superconductors from it. And just because we're actually doing something that nature already does, lo and behold, we're able to make some new phases that nature had sort of made already, which is to make these iron sulfide square lattices intercalated by hexagonal brucite type hydroxides like this. This is just an electron diffraction pattern of the square lattice that we're after, and then a hexagonal lattice that interleaves between the two as well. So you can see from the satellite reflections. And so Dave Manders talked about making heterostructures like Legos, and so perhaps we could make, through hydrothermal techniques as well, heterostructures of square lattices with hexagonal-based ones as well there. So that's sort of where we're going with next, and also working with my colleague here, JP, nice picture, and
I have other shirts.
Do you? And Jeff Lynn, of course, and these are some of our papers on these, and these are my students who do everything in the lab, and I just present their work. So anyway, thank you.